Hello, today we're going to talk about capacitors in series and in parallel. So before we start, I'll give a brief overview of what a capacitor is and why it's useful. So in a circuit, a capacitor is used to store electric charge. So you can see here an example of a parallel plate capacitor. So this is just one type of capacitor, but it's a good example. And so a capacitor is made up of two conducting parts that are close to each other but not touching. They're often separated by an insulator. And it's hooked up to a power supply, like a battery, and one of the conducting parts gains a positive charge while the other gains a negative charge. And what this does is it stores charge within the capacitors, so it's overall neutral, but the total charge it's storing is a magnitude of Q. And capacitors are useful in daily life because they have this ability to store electric charge. One example that you see often is in a heart defibrillator. So there's a capacitor there that's storing a charge that can then be released quickly in order to jumpstart a heart that has stopped. We measure the ability of a capacitor to hold a charge in a unit of using capacitance, which is charge per volt, or coulombs per volt, which is equal to farads. That's the unit we're going to use to talk about capacitance. And most of the time in real life examples, we use picofarads or up to millifarads. Just because 1 farad is actually a really large value and you won't have capacitors with a capacitance that large. Another way that we can measure capacitance when we're using a parallel plate capacitor, like in this picture over here, is using this equation. So this right here is the permittivity of free space. It's a constant that's given to us. This is the area of the parallel plates, or one of the parallel plates, and this here is the distance that's separating the two of these capacitors, the two of these conducting plates. And this can be used to find capacitance as well, and we'll use these as we now move on to talk about capacitors in series and parallel to help derive the way that they add together. So let's look first at capacitors in series. So here on picture A is 3 capacitors that are together in a series. And so we know that when you have things in series, voltage adds together. And so we can see here that our total voltage is equal to the V1 plus V2 plus V3. We also can use that equation from up above to find that voltage is equal to Q over C, so charge over capacitance, which is what we see being used right here. We can then substitute that in for each of these individual voltages as well, and we'll find that the charge will actually cancel out, leaving us with this equation right down here. And to rewrite that in a nicer way, we just do this and inverse it, and we find that 1 over the first capacitance plus 1 over the second capacitance, and so on with each capacitance in series, to the power of -1 is equal to our total capacitance. And you'll notice that this equation means that it will always be less than any of the individual capacitances in the series was. And another way to visualize this is shown in picture B. So rather than thinking of 3 separate capacitors in series, we can think of one capacitor that just has plates that are separated by a really large distance. And again, when we think about this equation from earlier, this makes a lot of sense because distance, when that gets bigger, capacitance decreases. And so that coincides with our equation right here that says the total capacitance of capacitors in series will be less than any of the individual capacitances. And so let's take an example, and we'll just use right here in A. Let me draw it out again in a circuit, because you'll probably see it like this on the test. So we have our 3 capacitors, which in a circuit diagram we just draw as 2 parallel lines. And we have 3 capacitors here, and we'll say that they have their capacitances of 3 farad, of 5 farad, and also of 6 farad. Okay, so take a second and pause the video, and using this equation right up here, figure out what the total capacitance of these capacitors in series would be. Okay, so now that you've had a chance to work that out for yourself, we'll do it together. So we'd have 1 over our first capacitance plus 1 over our second capacitance plus 1 over our third capacitance to the power of -1 would be equal to our total capacitance in series. And so if we plug that into our calculators, we'll find that the capacitance in series is 1.43 farad. Okay, so then as we move on to talk now about capacitors in parallel. And so again, to figure out how to find capacitance when capacitors are in parallel, we're going to use this equation of capacitance is charge over voltage. And we remember that the total charge when these are in parallel is added up. So it's the first charge plus second charge plus third charge is equal to the capacitance in parallel times the total voltage. And we can then plug this in for each individual voltage, right? So we have Q is equal to CV. And if we plug that in for each individual one, we'll find that voltage now cancels out of our equation and that the total capacitance of capacitors in parallel is just equal to the sum of each of the individual capacitors. So you can see that here in A, and then the other way to look at it is here in B. That the picture B, that if you have really large plates that are separated by the same distance, thinking about this equation again from earlier, the area has now increased, which means capacitance has increased. So you can think of 3 capacitors in parallel or more as just being capacitors whose areas essentially have been added together and make it a better capacitor, more able to hold charge. And so again, just like we did with capacitors in series, let's do an example of what this would look like on a test, how you might see this as a problem. And so we have our 3 capacitors in series. I'll just connect those all in. And we'll just use the same values for capacitance that we used up above. So 3, 5, and 6. And now what you can do is you can pause the video and take a quick second, it should be quick, to figure out what the total capacitance of these 3 together is. Perfect. So pretty easy, right? Because all we're doing is we're adding these 3 capacitances together. So 3 farad plus 5 farad plus 6 farad. In total, we get 14 farad as our total capacitance when they're in parallel. Okay, perfect. So that's capacitors in series and in parallel. And now to finish up, we'll just do one more practice problem where we combine the two. So sometimes in a circuit, you may have capacitors in parallel and capacitors in series. And when you see something like this, what you need to do is you need to break it down into its constituent parts. Okay, so first let's look at right here, this part where we have capacitor 2 and capacitor 3. And so again, we'll just use the same values that we used before. And first we'll look at capacitors 2 and 3, and are those in series or in parallel? Okay, so those are in parallel, right? So we're going to use our capacitors in parallel equation, which was, it's just the sum of the capacitances. And so in this case, that would be 11 farads, right? Because we have 5 farad plus 6 farad. Okay, and now we can redraw our circuit diagram to make this just 2 capacitors, C1, and one other capacitor that are now in a series. And this capacitor is the combination of capacitor 2 and capacitor 3 that we just figured out right here. Okay, and now our equation for capacitors in series is 1 over C1 plus 1 over C2 plus dot 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 to the -1, right? So in this case, we would have 1 over C1, which is 3 farad, plus 1 over our next capacitance, which is the combination of these two that are in parallel. And so right up here, that's 11 farad. And if we do that to the -1, we get that our total capacitance here for our 3 capacitors is 2.36 farad. And now we can just check our intuition here. 2.36 is less than 3, which is our lowest capacitance, which makes sense because in capacitors in series, the value will always be less. So that's a brief overview of capacitors in series and in parallel. I hope you learned a lot, and if you have questions, you can always look in the book to find more answers. Thank you.